You hear me now?
Yes.
Hey, I don't know if Daniel was feeling a little bit naughty when he did the schedule, but I've upset people in the past when I've presented here, and I even modified my presentation knowing that my topic was somewhat close to, although contradictory to what Near was about to present. So it's somewhat interesting that I'm following the Telnix guys talking about containerization, Anycast, and the operation of a network at global scale. I won't intentionally upset anybody. You will find many similarities now between my presentation and the previous one. There are also many differences, and the devil is in the detail. But if you go to sleep because you've just heard all of this, the one message that I would like everybody to take away is that we operate at layer 7, generally speaking, building applications, and we tend to forget many of the layers underneath, or at least solve the same problems that we solved 5 years ago in the layers underneath, forgetting that those layers have individually been progressing, and that many of the issues that we solve today in layer 7, we don't need to solve in layer 7 today, because they may have been solved elsewhere. In particular, they may have been solved in the network. And I'd like to talk a little bit more about that today. So Simwood's 20 years old, but during that time, we have had a 100% hardware refresh four and a bit times. And we've been going through one of those the last probably 18 months. So replacing everything from the network, bare metal of hardware, right the way through to our customer-facing application stack. And part of that journey is containerization, which I've got to be honest, I wrote off as a DevOps hipster thing a few years ago. It's been quite insightful, quite educational, being on that journey. And our reasons for doing it aren't the usual, the obvious. For us, it's more about development workflow, simplifying operations, enabling our developers to actually stand up and manage services rather than relying on 2 or 3 other people to create VMs, to create VLANs, all of the other stuff. But along the way, when the guys were presenting solutions to this containerization problem and the latest bleeding edge project, the one thing that always just struck me as bloody awful was this Docker bridge. Every project we looked at had this frickin' userland proxy with NAT, with various other horrible, horrible things that just seemed like a real backward step from where we were, and particularly in the world of SIP and RTC, just seemed like asking for trouble. So we got rid of it. We developed a plugin called Simwood Container Networking that completely removes it, and in essence enables us to give a public IP address to a container in just the same way as we could to a VM, but it gives us a bit more flexibility than that. And the benefits of that are that there's no voodoo, there's no NAT, there's no userland proxies, unless we want them. And there's certain applications, REST APIs, for example, where they may make sense. For SIP and RTC, they don't. We've also taken care of other operational problems, such as security. So when the dev guys create a compose file for a new container, they're not only specifying external ports that they want open, as they would in a standard Dockery kind of way, but they're specifying more granular rules that are automatically instantiated in IP tables. Coming to the question of service discovery DNS, we use console quite extensively, but the Simwood container Simwood network service automatically creates the DNS. So we get a host name, which is generally container name, availability zone, datacenter.simwood.com. And that gives us something that we can quite easily CNAME from our public DNS. So we can have 100 web server containers, for example, each with their own name, but we can alias that from public DNS. But the major benefit, and what I want to go into in a little bit more depth, is routing on the host. And if we go back to this little diagram here, it would be very easy to think that we are putting the container IP addresses on ETH0 on the external address of the host. We're not. The only address that ETH0, the external network interface of the host has, is its own, generally half of a /30 or half /31, the other half being the router or switch that it connects to. And the reason for that is because that host is acting as a router. When we create a container and we specify a public address, that address is created in the host, the kernel's routing table, and then we run routing protocols on the host itself so it can talk to the network and announce the addresses that it has. And if you run a trace route to one of our containers, you will actually see, obviously, you see the container as the last hop. The penultimate hop will actually be the host. You know, it is a proper router in the context of the path. Diving into that, oops, the joy of controlling things over 3G. Let's get rid of that. Diving into routing on the host a little bit deeper. In a legacy architecture, you used to have this notion of your edge routers, your big vendor, expensive boxes, then your leaf nodes, your access switches, and they would generally talk routing protocols to each other. And then you had this layer 2 domain underneath, where you would have hosts with IP addresses in subnets. They would discover other devices in those subnets through broadcast protocols. They had limitations both in terms of scalability and operations, so protocols were created to prevent some of those issues, spanning tree being one. If you go to the host actually being a router, you get rid of all of the problems that those create, and you actually introduce a mass of additional benefits. And that's as far as I'm going to go on that topic, because I spoke here last year on the way network architectures were changing and the flattening of network stacks. That's the top link. I did a deeper talk at ClueCon, if you want to nag Kathleen to get the video up. And I did ClueCon Weekly a month or so ago, which started very similar to this, but went deeper into the benefits of routing on the host. But I want to move on to something that routing on the host doesn't enable, because you could do it without it, but dramatically facilitates, and how that can help you in SIP architectures, and that is Anycast. So what is Anycast? Probably an unnecessary explanation, but given the audience. We're used to the internet operating with unicast, so an IP address generally exists exactly once somewhere on the internet, and you address it and follow whatever path is necessary to get to it. So in the example here, you might be going the long way to Slough because that's the unicast address that you're targeting. Anycast, that same IP address exists in multiple places, and routing protocols being what they are, rather than following the long path to the one specific place that address exists, you will follow the shortest path in network terms to where that IP address exists. So whereas in the extreme unicast example, you might hit Slough, in this case, in the Anycast example, you would hit Manchester if that is the topologically closest site to you. Best examples, with a couple of sort of funky long addresses for Ole's benefit, are Google's DNS addresses. Everybody knows those. You go to Australia, you do a trace route to those, they'll be a couple of milliseconds away. You go to LA, do a trace route to those, they'll be a couple of milliseconds away. Why? Because those addresses are announced and available in pretty much every data center that Google has, using Anycast, and Anycast gets you to the closest one. So the key benefits of it are a really locality in network terms. And from the locality, you get two other benefits. One is load balancing. If everybody around the planet is hitting their closest node, you're naturally distributing load around the planet. The other one is redundancy. If everybody's hitting their closest, if that ceases to be available, they still hit the closest. It's just not as close as it was before. They hit the next one. And by way of a little example, there's a view of our network post-Brexit, I might add, in terms of the scale. We've got our chap over here, somewhere in Eastern Europe, Asia. logically, he's going to connect to Tokyo. That's going to be topologically his closest site. Tokyo ceases to be online. He's going to swing over to London. Now, the important thing to note is that he's done nothing. He's not changed any addresses. We haven't modified DNS. He is connecting to the same IP address as he always was. It's just the routing protocols along the way for him to get there have determined that there's a better route because the previous one doesn't exist anymore. Where this gets more interesting, that's our UK network, and broadly we're in 11 data centers in the UK, but we tend to treat it as three availability zones. London, Slough, which is west of London, and Manchester in the north as a third. And our logic there is we can lose any one or even any two, and nothing materially changes until you involve customers. And in a unicast world, you might have an edge proxy in each of those availability zones, and they will have a distinct address. You might give them DNS. You might manage that DNS to swing customers to where you want, but you can't control them implementing things in the way you recommend. So you cannot control a customer connecting in London, forcing his traffic to, say, Manchester. Now, as it happens, we're a massively well-peered network, something like 650 peers, so 650 other ISPs where we're a single hop away from them. 86% of our traffic comes in over peering, very little goes over transit. So we're quite well placed to handle those issues, and we do to a large extent, but we can't control them as well as we'd like. So what you find is you've got three availability zones, but it's not impossible for a customer to create a situation where they're dependent on all three, such that you have an issue in one site and it's guaranteed to affect them. So what you've achieved by having multiple availability zones is 3 times the likelihood of a problem and an assured impact when it does. Anycast enables us to deal with that because Anycast will ensure the site the customer hits first is the site that they get service from. End of. The others become redundant high availability sites for that customer as we intend. So how could this be used in a SIP world? Well, the example I've just alluded to is a stateless proxy. I gave the example of a global distribution of a single IP address. But given the global internet is somewhat dynamic, what you don't want to be doing is deploying stateful services in this way, because you don't want to be halfway through a dialogue and find that some ISP along the way has had an outage and the customer, rather than talking to Tokyo, is now talking to London, which knows nothing about the dialogue that's going on. Anycast at global scale works best for simple question and answer type transactions. That's why it's so good for DNS. It's also actually pretty good for HTTP nowadays. But for prolonged SIP dialogues, probably not so good. But if you want to do, say, a SIP redirect to the closest unicast proxy, it's very good for that. Simple question and answer, doesn't matter what happens after that. But you can do stateful services with Anycast if you're careful and conscious of its limitations. So there's a picture of a typical POP, and if we actually look at the hosts, look at the leaf nodes, there's multiple paths to any one of those containers on any one of those hosts. And what you don't want is a container is a customer hitting 20 different hosts in the course of a transaction, because you'll have the problems I just alluded to. What you want is to stick a customer to one host or to one container, but still get the distribution. And thankfully, you can achieve that with routing technologies. One such technology is this thing called equal cost multipath. So your switches above your host have multiple paths to an IP address, because that IP address exists on multiple hosts. They are all the same cost, because all those hosts are the same distance away from that switch that they're directly connected to. And in a very, very similar way to the dispatcher module with SIP, your switch can hash flows and make those flows stick to certain hosts. So all of a sudden, you've got one IP address that can be on 1,000 hosts, they can be connected to the same switch stack, and your switch is doing your distribution of stateful services across them. In an environment where the network doesn't normally change, i.e. your private network within a data center, that is a really powerful technology, and you can take the same image with the same IP address, replicate it 1,000 times, and let the network take care of distributing load across it statefully. So you can take your usual dispatcher host, for example, and have n times n of it. But you can also use this for service discovery. I mentioned, I think, to answer your earlier question, we use Console. We also automatically manage DNS, and that is useful in many ways, particularly where you're using service discovery externally. You can just CNAME a host and then manage where that goes internally. But if you think of Anycast, if you say my Redis host is always ... to, wherever in the network I am, suddenly your service discovery requirements become dramatically simpler. Really, you just need to know what IP address Redis is on, and DNS solves that problem perfectly well. But the point is, with Anycast, that address never needs to change. For read-only services, take Redis, for example, you can deploy it 1,000 times around your network and rely on the network and Anycast ensuring that the queries to that host always go to the closest node. Doesn't work, obviously, if you're going to be writing to random Redises. You would still want to write to your master. But certain other clusterable technologies, you can write to any node, and they'll take care of it. So take a simple example here, too, and this is a typical example for us. We separate generally voice and media nodes from generic compute nodes, but we consider signaling to be generic compute. So this is a generic compute node. It has a Kamailio instance, and it has a Redis instance, which is queried by it. Because the host is a router, that Kamailio will always use its local Redis, even though both Kamailio instances are configured with the same IP address for Redis. And this solves a massive service discovery problem that in our evaluation of containerization technologies, nobody could ever answer for me. My problem was quite a simple one. If I have Kamailio on this host, why the hell am I querying Redis on that host? And if I've got Kamailio on that host, why the hell is it querying Redis on this host? It's completely pointless, completely unnecessary. It's a waste of everything. With routing on the host, and in particular Anycast, that Kamailio will always query its closest Redis. But in the event of its closest Redis failing, it'll query its closest Redis, which happens to be the one on the next host. And if you take that a stage further, you could actually lose all of your Redises, or is it Redeye, I don't know, in a given data center. And without changing the IP address, without changing any DNS, without doing anything in service discovery, suddenly be querying ones in a different data center. And guess what? It'll be the next closest data center. That brings you on to something that I call Anycast, which is using Anycast for HA of stateful services, which is kind of, depending on your viewpoint, sort of the Holy Grail or Satanism, depending which way you look at it. If you take a stateful service, say B2B UA, so you've got a free switch node up in, say, London. Unlike ordinary Anycast, you need a backbone, you need connectivity between the sites, and over that you would share state. But as you know, free switch, you can keep the call DB in Postgres or something, share that across multiple nodes, and recover a failed node on any other. But to do that, you need to swing an IP address across to it. And generally, your options there are people ID and other stuff, which restricts you to a layer 2 domain, which will generally be local. You can scale that internationally, but you'd probably be locked up as insane. Using Anycast, you can configure as many free switch nodes as you want with the same IP address. Using routing protocols, control which one is the primary, and then if your primary fails, you can use your deputy. And all free switch has to do is identify that it is now the new primary, and recover state. And if that one fails, you can swing it over to a third one. And you can do this globally. And I'm not talking here of doing this with your one big edge proxy that you have 2 instances of, as you might think of HA. I'm talking of doing this with 1,000 free switches in all different places and it being a routine method of deployment. And I hope to do that as a dangerous demo at ClueCon. So we'll see if it works. But sort of in our lab, in testing, this works. The other Anycast deployments that I've mentioned are live in deployment at Simwood with good results. And I'd encourage you to, as I said at the start, just think, when you're developing at layer 7, just think that some of these problems that you're solving might not actually need solving at layer 7 because they've probably already been solved at the lower levels, which have themselves been developing over recent years. Uses for that, anything stateful. So registrar, B2B UA was the example that I gave. RTP proxy, RTP engine. Now, Kamailio RTP proxy or RTP engine have a method of sharing state and swinging the primary over, but what Anycast gives you is the ability to not need to reconfigure an IP address. They just sit there, exactly the same image with exactly the same IP address. No layer 2 constraints, no voodoo involved in doing it. And that's me. I don't know if I'm massively under time, but are there any questions? Uh-oh.
Hi, great talk. We should talk after, by the way. Have you had to deal yet? So presumably you're announcing your space out from all of your POPs. And with Anycast, have you had to deal yet with losing multiple nodes and then having a flood of traffic going to the remaining?
Well, I disagree with your premise. So we do announce all of our space at all of our POPs. At the same time, we don't. Okay. So generally what we do is our IP prefixes are geographically segmented. So a given /23 will represent a specific availability zone. That /23 will be announced in that availability zone, but we'll also announce the global /21, global /22 as well. So in the event of a given availability zone dropping off completely and ceasing to announce its /23, obviously the most specific prefix will then be the global /21. From an architecture point of view, I showed the map of the UK. We dramatically over-specify everything, and we're quite fortunate. So much of our traffic comes in over peering that it's business as usual to give a customer a 10 gig port, even though they're sending 100 mega SIP traffic. So every one of our POPs can carry all of the network's traffic. So that's not an issue.
That's what I was curious about. Okay, thank you.
Okay, and just as a reminder for SIP traffic with Kamailio, if you want to randomly reject or redirect, better said, if I remember correctly, the guys from 1&1 a couple of years ago, they added good contribution on selecting some registration and sending redirects to other nodes eventually, depending on your architecture. So there are some solutions there when you get like waves or tsunamis of traffic to redistribute it over a period of time. So I don't remember, maybe it was Henning like 5-8 years ago that added a contribution to the registration module in Kamailio. So apart of just looking at the IP layer, there are some solutions in Kamailio just for the SIP traffic. Other questions as I just jumped in here? One. Armin.
Hello. I have a question about, the clients that you had were all presumably like SIP phones or something along those lines trying to access your Anycast addresses. From the looks of it, that's kind of what it looked like. Is that true? Or?
Yeah, we're wholesale. So it's typically ITSPs. So it's typically their proxies, but we do see some end user stuff register directly against us. We also see media directly where they just bypass it to us.
Okay, so I had a specific question about the hashing algorithm. So in SIP trunks, where you have sort of your quad IP and port pairs being the same, won't those all hash to the same host onto your network?
The answer is it depends. So just as the dispatcher module has different hashing algorithms, each different chipset has a choice of different hashing algorithms that you can apply. So we use Arista, and that from memory has got something like 8 different hashing algorithms. The default is, like you say, source destination IP address, source destination port, which actually at the scale you're kind of doing this tends to work, but you can get more granular than that and do it in different ways.
Okay, one more here and another one, Catherine, afterwards. Sorry, I'm not taking lady first.
Yep. Hello. So you've talked about the benefits of Anycast. Have you encountered any problems or any of the drawbacks? Like, why are the roses so red and not? Then why is everybody else not followed over?
Yeah, there's many benefits, and it would be wrong to take this as a go home deploy Anycast. It's a silver bullet to all your problems, because reality is it will cause you more problems than it solves unless you're very careful. There's a few issues with it. A fairly obvious one is monitoring. All of a sudden, you've got 1,000 services with the same IP address. So if you're monitoring that in a traditional kind of way, i.e. ping that IP address or check the return from the service on that IP address, you're not going to know of any issue until the last one fails. And then you've got 1,000 times the problem you had before. There's obviously ways around that, monitoring internal addresses, et cetera, et cetera. The other one is other networks. I mentioned that I was careful to say that the address that you hit is the topologically closest one, not necessarily the geographically closest one. And for us, that's less of an issue because we're so heavily peered that generally another ISP is one hop away from our POP, and that POP can deliver service. But where you are relying on transit and announcing internationally, you get silly things happen. So there's certain tier 1 providers, or they call themselves tier 1 providers, but the club has been very reluctant to let them in over recent years, that like falling out with people. And every time they fall out with people, they do batshit crazy things with their routing. So you could actually find that from Amsterdam, if you were using them as a transit provider, your topologically closest node transits New York. So in that respect, it can be counterproductive, but you've got to be aware of that. And the trick to that is using some of the tools in the routing arsenal, like, say, communities, and telling that particular transit provider not to announce your space in the US, only announce it in Europe, or only announce it in Asia, or don't announce it to this particular network. But it is true to say that there's another layer of problems and management that you never thought you had, and you possibly don't need. But the benefits of it, that your customer can be anywhere on the planet and always hit the closest node, always get the least latency, and it follows the most predictable network performance, is good and is worth it. But the benefits on your network for service discovery, high availability, are probably actually bigger than the global benefits.
I don't have a question, just to let you know, it has been published. If you would like to watch your previous talk, you can go to YouTube/research.
5 minutes?
No, it's been up for like a month.
Oh, okay.
Okay, then thank you, Simon. It's time for a next coffee break, and I think Randy wanted to give that T-shirt now.